Hi, and welcome to Learning 3D Character Animation with Jeff Liu. I'm Jeff Liu, and let me tell you a little bit about myself. I'm a self-taught animator, and I've been working in the CG industry since 1997. Before that, it took me about 1 to 2 years of full-time studying and practicing on my own before I got my first full-time job doing 3D animation. Hopefully this DVD will help you get to that level much faster than I did. I fell in love with 3D character animation the moment I started doing it. I couldn't believe the power and flexibility of CG. You can create something out of nothing. You can turn your ideas into something others can watch and enjoy. So what does it mean to be an animator in the CG industry? Well, you must never stop being a student. You can never stop learning. This industry and technology moves so fast that if you don't keep up, you'll be left behind. The ones who persevere and keep working at their craft will be successful. 3D character animation is twofold. On one side, you have the artistic ability. On the other side, you have technical proficiency. This DVD focuses on the practices and principles in creating good character animation. You will develop faster and be more disciplined in your craft if you have an understanding of how things work and the reasons behind each principle. It's a long road, but I hope this DVD will somehow inspire you and support your quest in becoming a character animator. Before we start talking about animation, let's talk about the world space. The world space is the virtual world in which your 3D characters would exist. It has 3 dimensions. The first dimension is the x-axis. If you're looking directly at your screen, x runs from 0 to positive infinity or 0 to negative infinity going across your screen. And depending on your units, could be centimeters, inches, feet, or whatever, wherever you are on this axis would give you a value of like positive 15 inches or negative 35 feet. But you can never leave that one dimension. Let's bring in a second dimension. Now the y-axis goes straight up or straight down. Positive going up, negative going down. And combining x and y, it'll give you this plane. So if you go 5 units in x and maybe 10 units up in y, you're going to be over here. It's going to be that coordinate. But you can never leave this plane. That's where the z-axis comes in. Z is the depth. If x is going across, y is going up and down, z is going to go straight towards you and straight behind me. Positive towards you, negative behind me. Now instead of a plane, it creates a volume now. So instead of this plane, you could be over here or you could be back here. You could be in any one point in this world now, but that will give you a value of x, y, and z. Okay, that's how the 3D software keeps track of where your object is at any one point in time. It's very important to know this coordinate system because computer animation is very mathematical based. Now fortunately, we don't need to know the math behind the animation. The computer does that for you. But it's very important for us to know which way is positive y, which way is negative z, or positive x, because the tools you'll be using later on would depend on the fact that you know which direction is which. Computer animation differs from traditional animation and claymation in terms of world space. Because in traditional animation, you draw your figure on a piece of paper. And that's a very relative world space. In claymation, you animate the figure in front of you on the table or the stage, and that's a very relative world space also. In computer animation, your world space is infinite, going from the center of your world at 0, 0, 0 to any infinite direction. So say at 1 second, your object could be in this point in time, and 5 seconds later, your object could be over here. So going a course of 5 seconds, your computer will interpolate for you going from this coordinate to this coordinate. And that's a very simple animation. But as your animations get more complex, you'll realize the importance of knowing what the world space is. Picture this. there's a person standing in the center of the world space at 0, 0, 0 for X, Y, and Z. And in the palm of his hand is a little bug. Now, to this bug, this hand is the entire world. The bug knows nothing outside of this hand. So to him, he's in the center of his own world at 0, 0, 0. Now, say the person takes 10 steps forward and then 10 steps to the right. Now, his position is 10, 0, 10. What is the position of this bug? Well, he still thinks that he's in the center of his own world. So he thinks he's at 0, 0, 0, and that's his local position, dealing with this local world. His global position is going to be the same as the person, pretty much 10, 0, 10. And that's the difference between local position relative to this local world and global position, which is relative to the entire world space. This happens when two or more objects are in the same hierarchy. We call one object the parent and the other the child. Now, it's not taken in a literal sense where this person gave birth to this bug, but it's more of a way for us to define the status level of these 3D objects. A child is any object that is below another object in the same hierarchy. A child's motion will always be affected by the parent's motion. A parent's motion will never be affected by the child's motion. Try to think of it in terms of something like a kangaroo, where the parent is carrying around a child in its pouch. So wherever this parent went, this child had to go. But the child was freely able to move about inside this pouch, and it didn't care where the mom went, and it was pretty much oblivious to where the mom's going. But wherever he moved inside the pouch would be his position, would be the position in which he thinks that he is in. Now, a hierarchy could be more than two objects. It could be 3, it could be 10, or it could be 2 billion objects. And each child doesn't have to have another child. Each child can have a sister-like person, which is in the same level as this other child, this sibling. Say we have one parent. It can have 2 children that are in the same level in the hierarchy. So if you move one child, the other child's not going to move. Unless you put this third child underneath the second child. Now, the third child becomes the child of the second. So now the second becomes the parent of this third. Let's describe it in terms of color-coded balls for easier understanding. Say we have a green ball, a blue ball, and a yellow ball. We put the blue ball underneath the green ball. So now the blue ball is a child of this green ball. And now we put the yellow ball underneath the blue ball. So now the yellow ball is a child of this blue ball. If we move the green ball, both the blue ball and the yellow ball move along with it. If we move the blue ball, only the yellow one moves, and the green ball is not affected because the blue ball is one lower in the hierarchy than the green ball. If we move the yellow ball, nothing else moves with it because the yellow ball has no child, and the blue ball and the green ball are both parents of this yellow ball. So let's rearrange this hierarchy. Let's take the yellow ball out of the blue ball and place the yellow ball underneath the green ball. So what do we have now? We have the blue ball and the yellow ball being in the same level in the hierarchy. If we move the green ball, again, both the blue ball and the yellow ball move. But if we move the blue ball now, only the blue ball moves because it has no child. And if we move the yellow ball, only the yellow ball moves because it has no child. And the blue ball and yellow ball pretty much are independent now. They're both children of this green ball, but they have nothing to do with each other. Now there's a name for this green ball. The green ball, no matter what configuration we do, as long as the green ball is the top parent, if it's the top object or top node, it's called the root. So wherever we translate this root, everything else has to go. And this green ball will always be the root unless we put this underneath another object. Then that object becomes the root. So a root has no parent. Anything in 3D can pretty much have this parent-child relationship. You can have 2 empty null sets or 2 locators be parent or child, or you can have 2 models be a parent and child, or you can mix it up. You can have a bone being the parent and a model as a child, or vice versa, or however you want. Now in terms of character animation, we're going to talk in terms of bones. So let's take an arm, for example. We're going to divide it up into 3 bones. We're going to divide it into the upper arm, the lower arm, and the hand. If we move this hand and we don't move this lower arm and upper arm, there's nothing that's going to happen to this lower arm or upper arm because this hand is the lowest node in the hierarchy. It's the lowest child. It has no effect for this part or this part because these are both parents of this hand. Now, if we animate the lower arm, it's going to have an effect on this hand because this hand is a child of this lower arm. So wherever this arm moves, this hand has to go with it. And it's going to have its own independent little twiddling animation around. Again, the upper arm is not affected because it's the parent of these children. Now, if we move the upper arm around, it's going to affect everything down below it. It's going to affect the lower arm, it's going to affect the hand. And in our case, in this three-joint object, this upper arm is the root. Wherever we translate it, whatever we do to it, it will affect also all the children underneath it. If we now look at the entire body, it's usually the hip joint that is the root for the entire character. So that means when you want to translate the entire character around, you usually grab the hip joint. And all bones are in some way connected to those hips. Going up from the hips is the spine, then splitting off to the two arms and going up the neck and the head. And also going down from the hips are the two legs. If you look at the two legs in a hierarchy, they should be in the same level in a hierarchy. And if you look at the two arms, they should be in the same level in the hierarchy also. So that means that you can animate one arm independently from the other and one leg independently from the other. Since we're talking about the entire skeleton, the next topic is going to be character setup. And we need to do this because without a character, we can't character animate. So bear with me, all right? Character setup is a very in-depth topic, and it deserves its own training video all on its own. But it's very important for a character animator to know character setup, because when you're animating a shot and you find that it's very hard to animate a certain move or a certain thing that this character has to do, sometimes it's easier to adjust the character rig than animating the hard way. Now, before you set up a character, you have to look at what your character looks like, what your character is going to be doing in the animation. Is your character a cartoony character or is he photoreal? It all depends on these questions, what the skeleton will look like inside his body. The method of character setup is different in every software package, but the idea is the same. The basic idea is that you have a 3D model of a character and you insert a skeleton inside to control this 3D mesh. So for example, if I have an arm and I insert some bones in the arm, then I assign some of the polygons or some of the NURBS control points or the spline control points to this bone in the arm. Wherever I move this arm, those points will follow. You would do that for the entire skeleton, so whatever limb you move, those points on the mesh should follow that limb. You can always tell when a certain point in the mesh does not belong to any bone when you drag the entire body around and you see certain points sticking out like spikes. That tells you that these points don't belong to anything and you want to reassign those points to whatever bone they're supposed to belong to. Now, the skeleton shouldn't be anatomically correct. If you're setting up a skeleton for a humanoid character, there's no way it should be anatomically correct in terms of the amount of bones because there's just so many bones in the body. We want to keep things simple because in animation, if we have fewer bones, that's fewer bones to pose. If we have 100 bones to pose, on each keyframe, we're going to have to rotate 100 bones. And that's not too fun. To have a fun animation, the fewer the bones, the faster you can animate. But you should be careful about having too few bones. You should have enough that you can deform your character to look anatomically correct. Now that's the key. You want your character to look anatomically correct, but you don't want the underlying skeleton to be anatomically correct. The things you got to look out for are where the joints are positioned in the body. So you want to be able to rotate your limbs in the correct manner. You don't want to have an elbow joint over here. You want to have it over here. Looking at the spine, there's a lot of vertebrae in the spine, and we don't want every single one in our character. I usually like 3 to 4 bones in a skeletal spine. I believe 4 gives you more than enough. 3 is pretty good also. You just want enough that you can easily bend your character and make him look flexible without creasing your model in any way that it's not built for. If you look at a human spine, if you look at in any textbook, you'll see that the spine is curved, like an S curve. You don't want to set up your bones in that manner. The reason for that is because when you do a twisting action with your bones, if your bone is angled like this, if you have an S-curved spine, rotating it in this axis is going to rotate your chest at an angle, and that's not natural. You want to have a spine that's more straight. So when you rotate your chest, it's going to rotate the way you want it to. It's going to look anatomically correct, but it's not really anatomically correct. Now, talking about some other joints, the biggest problem usually for characters in 3D are the shoulders, because the amount of rotation that you need in your character is very difficult to get in 3D. In a human, it's a ball and socket joint. It's very articulate. You can move this like crazy. You can move it anywhere you want. In 3D, the bones are really pulling the points on that model. So if you have any twisting motion, it's not really the skin sliding over the muscles. It's really the bone directly controlling the skin. It's going to give you pinching. Sometimes, if you can avoid that complex shoulder, the better. If you can design your character with, say, detachable arms, maybe give him armor or some sort of shirt where he can twist any way he wants and you don't really see it. You don't really see the error in that shoulder. Another solution for the shoulder area is to split off joints. This is another case where a character is not anatomically correct. If you look at the arm, usually we have one joint going from here to here and another joint going from here to here. But if you wanted to avoid this pinching problem that you get usually in the shoulders, we can add a joint in the middle. So have a joint going from here to here and then here to here. So this joint will take care of this type of rotation, and then this joint will take care of this rotation and this rotation. And that's one way in 3D how we can avoid known problems. Another case where you might not want to be anatomically correct is when you want to add certain bones to do certain functions. Say you have a character that likes to spin around, that likes to jump up in the air and do somersaults and flips and crazy spins. You might want to add a bone for the center of gravity, for the character to spin around that center of gravity. What we talked about before, having the hips as the root, if you rotate around that root doing a somersault, that doesn't look correct in terms of spinning around the center of gravity, because a character's hips might be pretty low, especially if your character has short legs. If you're going to rotate around his hips, it's going to look lopsided. So if we have another bone for the center of gravity, that character can spin and rotate around this center of gravity bone, and placing that pretty much where the center of gravity is for that character, and it can have natural spins and twists and whatever. Now that means the hips are no longer the root for that character. This center of gravity bone is. And that's very tricky. The more bones you add, the more you have to worry about. Now the key for a character setup is to keep your character setup simple. So when you're animating your character, it's going to be easy, it's going to be fun, and you're not going to get too burnt out from animating, because the more bones you have, the more things you got to keep track of, and the less fun it gets. It becomes pretty tedious. But keeping a character simple doesn't mean to have as few bones as possible. You can have a very complex setup, but you can also have very few controls to animate that character. One case of a complex setup making your life a lot easier might be in the hand. If you look at the hand, there's just so many joints you have to worry about, and animating each joint in each finger is going to be very tedious. So if you know in your animation that you just want the hand to be open and closed in a fist, you can make a slider. So for example, the slider at 0 could be a closed fist. If the slider slides to 100, it'll open up the hand. Slide back to 0, it'll be closed. Now this is another case of making your life a lot simpler with a very complex setup. Actually, setup's not that complex. This is something you'll learn later on when we get more into detail about the animation principles. If you've already been animating, you're probably running into a problem where your feet go through the floor or your hands penetrate through something you want to hold on to, like a table or a cup or something like that. There's a feature in most software packages. Almost any character animation package should have a feature called inverse kinematics. Now, what we've been talking about before is called forward kinematics, where, say you rotate the shoulder, then you rotate the elbow, then you rotate the hand. Now that's in a very forward direction, going from the top of the hierarchy down to the bottom of the hierarchy. In inverse kinematics, we can grab the hand and move it anywhere we want, and it's going to solve for this elbow and this upper arm to be in the position so that this hand is where we want it to be. So we could pull this over here, and these joints are going to solve. We could pull it down here, and these joints are going to solve. Now, there are many functions of inverse kinematics, but the main function is to keep limbs from penetrating or going through objects that you don't want them to go through. So the feet will stick to the floor, your hands will stick to the steering wheel, and so on. Another advantage of IK over forward K is that you have only one point to animate. You have this target, so you can translate this anywhere you want, and all these joints will be positioned to that target. In forward K, you have all these joints you need to animate now. That might be like 3 more things you have to animate over this one target. One disadvantage about IK is that if you happen to pull the target out too far for the limbs to reach, those limbs will snap pretty quickly, and that'll give you unnatural motion also. So you have to be aware of how far you pull your IK target, because the bones will not stretch. So be wary of how far you pull your IK chain so your limb doesn't overextend so quickly. Now, the greatest problem in inverse kinematics is you lose the natural look of the limb. So in forward kinematics, when we rotate, we get a natural arc. So if I rotate my shoulder and elbow, I get a natural looking arc, like I'm picking up something. With inverse kinematics, since everything is controlled by this end of the hierarchy, when we translate, we're no longer getting arcing type motions. We're getting linear type motions. If I translate my hand from here to here, it's going to be linear looking, and that's very robotic. It's not very organic looking. So that's the trade-off between forward kinematics and inverse kinematics. Now, you have to pick and choose what you want to best fit your shot. If you're going to be grabbing a lot of things, like if your character is going to be picking up lots of things or running all over the place, definitely use inverse kinematics. If your character is going to be flipping in the air, doing crazy spinning kicks, or just not touching anything with his hands, forward kinematics might be the better way to go. So probably the best setup would be a hybrid type setup where you can switch from IK to forward K pretty easily. Because in most cases, your character is going to be doing more than just walking and more than just flying in the air. He's going to be doing both. And you want to be able to switch from IK to forward K easily. Sometimes it's just a switch turning on IK when you need it and turning it off when you don't need it. Sometimes it's another slider type deal where you can smoothly blend from IK to forward K. And that's often the best because switching on and off IK, you usually see a popping motion. Say my foot is on the ground or my hand is on a table and I switch to IK once I get to that table, you're going to notice a simple little jitter, little glitch there if you're not careful about posing your forward K and IK at the same position. So using a slider type deal to blend from IK to forward K over a large number of frames, you'll get a less noticeable type of switch. The important thing is that you know the difference between IK and forward K and when to use them. For example, I usually like using forward K in the arms because I like to get that free-flowing rotational look to them. And I like using IK on the feet simply because it's easier to keep the feet from going through the floor. Another very important feature in character animation is the constraint system. Now, not all character animation software has constraints, but if your software does have constraints, that's a very good thing. Now, don't confuse constraints with rotation limits. For example, a limit would be where one joint can't move further than a certain rotation. Like my elbow cannot bend further than this. That's a limit. A constraint is a way to force one object to do what you want it to do at all times, no matter what. Some of the important constraints are things like the translation constraint or point constraint. Now, this constraint forces one object to be translated to the position of another object. For example, if I translate this blue ball to the green ball, wherever I move this green ball, this blue ball has to go. Now, this doesn't mean however I rotate this green ball, this blue ball will rotate. That's not the case. This is only translation. So if I rotate this green ball, nothing happens to this blue ball. Now, where would you use this translation constraint? Say you have a character who needs to jump in a car and drive around and then jump out of a car. Well, in the old days, before constraints, we would have 3 different models for this. We would have the character, the car, and a model of the character in the car. So you would do this by animating the character to hop in the car then turn off the character and turn off the car, and then turn on the model of the character already in the car. And when you move them around, it's just one model, so of course it looks like the character's in the car. Now, there's nothing really wrong with this, but it's an old way of doing things, and especially nowadays, it's going to affect things like special effects that you add to your character or motion blur for that scene, because on that instant, there's not going to be any motion blur. It also makes your scene bigger, and it's harder to organize that way. So with the translation constraint, you can constrain your character to the car, and then just move the car around, and the character will move with the car. When you want the character to get out of the car, just lower the enforcement of the translation constraint down to 0. And now your character and car can move freely by themselves. Pretty much in conjunction with the translation constraint, there is an orientation constraint or a rotation constraint. Now what that does is, say I have a blue cone and a green cone. If I orient constraint this blue cone to this green cone, it doesn't move anywhere. It doesn't translate anywhere. But if I rotate this green cone, this blue cone will rotate just like it. Now, where would you use this? Well, for characters, most of them have 2 eyeballs. And in the theme of keeping things simple, say you just want to animate 1 eyeball. So you can orient constraint the other eyeball to this 1 eyeball that you're rotating, and that's one thing to animate now, just that 1 eyeball. You don't have to animate 2 eyeballs anymore. And you can be sure that wherever this eyeball is looking, the other one's going to be rotating just like it. You can also use these 2 constraints when picking up objects. Say you have a character such as a bean who's going to pick up a gun. Now you would need to use 2 constraints. You would need to use a translation constraint to translate this gun to that bean's hand. And then you would need to orient constraint to orient that gun to follow the rotation of the hand. So the gun looks totally like it's in this bean's hand. The third important constraint is the aim constraint, and it pretty much does what it says. It forces one object to aim at something else at all times. So say I have a blue cone that's aim constraint to a green cone. Now you're going to see that this blue cone is going to point to this green cone no matter where I move this green cone. Now where would you use this aim constraint? Well, in character animation, let's go back to the eyeball animation we were doing, where the right eye was orient constraint to the left eye. Now say we had a scene where a character needed to look at certain objects on a table, and we wanted to make sure that he was really looking at these objects. Well, instead of guessing where these eyes are going to be looking by just rotating and estimating, we can tell it exactly where it should look by aim constraining the eye to a certain null or locator. So wherever we translate this locator, the eyes are looking exactly at that spot. Now there's other constraints like scale constraints or surface constraints or tangent constraints, things like that. They're not very widely used. Well, for example, surface constraints might be used for keeping objects on the surface of a model, maybe a teardrop or a sweat rolling down someone's cheek. Now the constraints I talked about earlier are very important in character setup because they can make your character setups very complex yet much easier to animate. For example, in IK, where it's kind of difficult sometimes to adjust the position of the elbow. Maybe it's erratic, it's random sometimes. So if you aim constraint your arm to point at a certain object, then it's easy to aim where this elbow is going to be at. And the same goes for the knees, to aim where the knee is supposed to point at all times. Also, going back to that walking animation with the head, maybe you can aim constraint the chest. So the head can look somewhere and the chest can move about wherever it wants. This is a sort of isolation type setup where different parts of the body are isolated from the other parts. So you don't have to really do everything in forward kinematics where the chest would affect the head. If you rotate the chest, the head has to rotate. This is no longer the case. You can aim the head and rotate the chest anywhere you want. And that makes life easier sometimes. Sometimes it makes it harder. It's up to you to experience these different tools so you know which ones to use on which animations. Another key thing about constraints is that it turns your rotational data into translational data. Let's go back to that eye animation. Instead of rotating the eyes, you're now translating this locator for where the eyes should be looking. It's much easier to look at translational data than rotational data because translational data deals with the axes we're used to, like the X, Y, and Z. Rotational data is somewhat more difficult because it's a combination of X, Y, or Z rotations. Now this is something we'll go into next using the graph editor. Now we're going to talk about the graph editor, which is sometimes called the curve editor. Now what the graph editor does is that it gives you a graphical representation of your motion curve by plotting out the data points. Now the graph editor is one of the most important tools in character animation, so pay very careful attention because you will live in the graph editor. Looking at the graph editor, it looks like any old type of graph.